All right, so let's get into 11.1. It's a pretty easy section, quite honestly. We're done with series completely. We have these two last topics, basically. We're basically toward the end of the semester here, which is really parametric curves and then a specific type of parametric curves called polar curves. If you're taking Calc 3, parametrically defined curves will be actually an important thing towards the end of the class. You'll have to parametrically define a lot of stuff. So let's get to it. Basically, today we're just going to see how it works, how it's set up. But the idea is that if you've got a point that's moving through space, sometimes you don't want to determine it by a function, right? Like f of x equals something. Sometimes you want to describe its x and y positions independently. And a lot of times we will do that as a function of a parameter. We'll set up a new variable and we'll say its x position is some function in terms of this new parameter. And the y position is also some function in terms of this parameter t. We usually call it t because the parameter is usually, but it doesn't have to be a generalized parameter. And really, technically, you can call it anything you want, but t is kind of the standard. So, in order to do this, we can basically write a function for each of the two different coordinates separately. So we can write something like x is equal to a function of t, and I'm just going to call it time for convenience. So x is a function of time, or at every different time, we'll tell you what its x-coordinate is, and y is a different function of time. So at every different time t, this function will tell you what its height is. And these two things together, if it's a 2D thing, would be called the parametric equations of the curve. And just like, y equals f of x would describe the point at every spot x, this would now tell you the x and y values at every time t. And you basically get the same curve, it's just another way to write the curve. The nice thing about this method is you can have one variable instead of two or more variables. Okay, so I'll just mention that t is the parameter, as I guess we kind of mentioned already, and each value of t points to a point. So each value of that parameter t points to one xy location. The cool thing about parametric curves is now you can actually define things that are not functions in this manner, even things that overlap. Imagine you had this. You can never describe this as a single y equals f of x function because there's 2 points on, well, there's many problems, but there's 2 points on the same curve that are, the exact same. How would you differentiate them? But now with parametric, we just say, all right, well, the first one happened at time t equals 5, and then it kept going around the loop, and then at time t equals 10, it got back to the same point. So it's all sorts of complicated stuff are no problem to define in terms of parametric curves, which is why they're actually very useful. Why you see them in Calc 3 so much is because everything that you do in 2 dimensions in Calc 1, we're now going to do in 3 dimensions. And so in order to integrate and stuff at the end result of those things, we really need it down to one single variable. All right, so we're not going to worry about Calc 3 today, but let's just worry about the basics. Suppose we are asked to sketch a parametric curve. So sketch the curve that is going to be defined by these parametric equations. X equals t squared minus 2t, and y is equal to t plus 1. So one thing we could do here is we can set up a table of values and plot it out. That's the first basic idea of how to plot anything that we don't know how to graph yet. So what we'll do is we'll now have a chart that's going to be 3 columns, basically all the times. Normally when you graph these things out, you'd have all your x values and then the y outputs that would occur from a function. Well, now we'll have a time input and the x and y coordinate that basically goes along with each of those things. Now, how do you know exactly which times to pick? I'm just picking ones that are actually going to work out nicely. Suppose we plugged in time t equals -2. So if I plug that into x, I clearly get -2 squared, which is positive 4. -2 times -2 is another positive 4, so I get x equals 8. If I plug in -2 down here, -2 plus 1 is -1. So we could start actually graphing it over on this side. We might want to go up to 4 in the y direction and maybe over to 8 in the x direction. Okay, so our first point was 8, -1, which was down. And this occurred at t equals -2. Right? That time corresponds to that point on the graph. Now, we wouldn't know from that point that it's going to be going this way, but I do, so that's why I made the axis in this orientation. Obviously, you'd have to scale it once you saw what was going on. area says, can we always use these numbers for t? No, absolutely not, right? Different things will have different things that would make sense to plug in. However, ultimately, our goal is not to do plug and chug like this, just like any graphing stuff, right? The first time we see a new graph, we might plug in points to see what happens. But then after that, we learn what its shapes are and how it is better to graph it in a generalized fashion. So this is just exploration, really. You're not really going to want to do this unless that was a last resort. And the reason for that is exactly basically what you mentioned. You would specifically know what the best t values to plug in would be to give you the picture of the graph that's important. All right, so let's plug in -1. You get -1 squared is +1. -2 times -1 is +2. So 1 plus 2 is 3. And -1 plus 1 is 0. So at time t equals -1, we've moved all the way over to 3, 0. So this is t equals -1 here. We'll connect the dots in a second. If I plugged in 0, I obviously get 0, 1. So now we're up to this spot. This is the t equals 0 location. If I plugged in 1, I get 1 minus 2. So that's -1. 1 plus 1 is 2. So that's now over here. T equals 1 location is there. If I plug in t equals 2, I get 2 squared minus 4. So that's 4 minus 4 is 0 again. 2 plus 1 is 3. So that's 0, 3. So I have this point, t equals 2. So notice you've seen this thing now bend to a certain negative spot and then kind of bend backwards towards the first quadrant. And that's going to continue along. We'll do one more point here. If I plug in 3, I get 3 squared, 9 minus 6, so that's 3. And the y coordinate would be 3 plus 1, which is 4. X 3, y 4 would be up here. That's my t equals 3 spot. And you can see that basically this thing looks like a parabolic shape. Or to connect all these dots, it looks more or less like that. Now, of course, this is not really the ideal way to graph something because, how do I know that -1 was the vertex spot? Yeah, you don't know. Maybe it went a little further. You don't know exactly unless you plot every point. But we'll get to a more generalized way of graphing in a second. Any question with the idea of what a parametric equation looks like? That's really all we're after at this point. We just have different times that correspond to different points on a curve and make up the whole picture of it.
How is it possible that time is negative?
Well, that's a good question. So if it was literally representing time in a specific example, like I said, the parameter really could be anything. It could just be a generalized variable that accounts for both different of the two variables movement. So yeah, if it was physical time, we wouldn't really want to think of it as negative, although sometimes it could. Sometimes you could think of it like time as like the moment of an explosion. So time positive would be moments after the explosion, time would be moments before the explosion. So it actually is possible to set up things where there's quote unquote negative time if you're just looking relative from an event. Good question. Now the other thing that parameterization can do, actually I'll talk about that in a second. Let's talk about a better way to graph things that is more consistent and more of an actual process than this kind of random picking points. And usually what we try to do is to eliminate the parameter. So eliminate the parameter to graph, I'm going to say, more systematic. This might not always be possible, but what it is, and pretty much always is going to be in Math 112, it's the way it goes. So I'm going to put here by substitution, I'm going to put a question mark next to it because sometimes you do a little bit of different things to eliminate the parameter, but substitution will be like the main obvious one. So we had these parameterizations, x equals t squared minus 2t, y equals t plus 1. So by eliminating the parameter, I just want to write this without any t's in there. So I could just solve for one of the equations, right? This one's pretty easy. Solve for the parameter in terms of the other variable and then plug it in. So t is clearly y minus 1, and I could take that and plug it into the first equation. In which case I get x is equal to y minus 1 squared minus 2 times y minus 1. So you can see now we've written it as a single equation, x and y, with no parameter at all. So let's FOIL that out and see what it comes out to be. X is equal to y squared minus 2y plus 1. If I FOIL out that first piece, distributing the minus 2 into the second piece gives me minus 2y plus 2. And just simplifying stuff here gives me x equals y squared minus 4y plus 3. And that should make a lot of sense based on the graph that we had, because what is x equals, y squared function, basically? That's just a sideways parabola, which is exactly what we saw. It's a sideways parabola opening to the right. Now, you may actually at this point have a quick question of what's really the point of having the parameter and separating this into two equations when I could have just written the sideways parameter I always knew all along? And there's a couple different advantages. Number one, sometimes the thing that you're graphing cannot be expressed as a function, either as a function of x or as a function of y. So the only real good way to write it would be in a parameterization sense. Second reason is the Calc 3 reason, where sometimes you just need everything in terms of one single variable. That won't come into play in our class. But the third reason, which is easy to understand in a physics sense, is the parameterization now gives us a direction of motion, whereas just the static function, right, this curve is just what it is. But now we know that this thing is actually moving from lower time this way. I'm going to put some arrows to show you the direction of motion. So a lot of times the parameterization problem will be something that mirrors the motion of a particle through space or something like that. And from lower to higher time gives you the direction along the curve that the thing would be traveling. So there are actually a lot of reasons why you would want to do parameterization, even if you could graph the thing very easily as a function. So what we're going to do now is essentially come up with a few different techniques for eliminating the parameter. Some of them are not as obvious as just direct substitution. How about this one? And a lot of times this will refer to something like find the path represented. So when they talk about the path, it's not just the graph, but it's also the direction that, say, a particle would travel along this particular graph. And sometimes it's not just, left or right. Well, you'll see. There's some interesting things that can happen. So find the path represented by x equals cosine t, y equals sine t, on the range t going between 0 and 2 pi. So trig functions always are going to lead to some interesting stuff. How would we eliminate this parameter? Now, I get into inverse sines and cosines, which I don't really want to. It's going to be very hard to solve for the parameter and plug into the other one. So here is the trick that you can aim for if you see sines and cosines or really any trig functions. I'm just going to title it Eliminating the Parameter, t in this case. And what we're going to do is we're going to try and take advantage of Pythagorean theorem, because I know cosine squared plus sine squared is equal to 1. So if I were to square both of the sides of both equations and add the two equations, I would have cosine squared plus sine squared, which would eliminate the entire parameter when I used Pythagorean theorem. So squaring the first equation is x squared equals cosine squared t. Squaring the second one gives me y squared equals sine squared t, and then we add them together. So obviously on the left side, I get x squared plus y squared. On the right side, I get sine squared t plus cosine squared t. But by Pythagorean theorem, that's just x squared plus y squared equals 1. I don't know if you need to really write this, but if you do, I'll just note that it's technically Pythagorean identity. Right? So that's the graph. Hopefully, actually, everyone recognizes that. What is x squared plus y squared equal 1? Yeah, it's a circle, right? Circle, centered at the origin, radius 1. So we now know what the graph looks like. It's something that's part of this path, right? With a radius of 1 and centered at the origin. However, we can't just satisfy ourselves there because I have a range, 0 to 2 pi. So I know that the thing is moving around on this particular graph, but it's possible it might have only gone from 1, 0 to 0, 1, right? Only a portion of the graph. Or it's possible it did even more than that. So we're going to have to plug in these values to see what actually is happening as I travel around the circular path. So let's find the initial point. These problems are not very hard, but they take up a lot of space. So I'm traveling from t equals 0 to 2 pi. So the initial point's t equals 0. So when t is equal to 0, I just plug in. I get x is equal to, well, cosine of 0 is 1, right? If I plug in for y, I get sine 0, but sine 0 is 0. So the initial point is 1, 0 right here. So that's where the particle starts. I don't know which way it's going yet. It could be going up and around or down and around. But let's take a look at the terminal point. Actually, we don't really need to. The terminal point will be exactly the same, right? We plugged in 2 pi, cosine 2 pi, sine 2 pi. That's the exact same spot. So I'm not going to write it out, but the terminal point is the same exact point, 1, 0. That's going to be essentially what we've done. 0 to 2 pi is one period of these trig functions. We've gone around the circle exactly one time and gotten back to where we started. But which way did we go? So let's figure that out. I'm going to put a plug-in for the direction. What would you suggest as a t-value to plug in to figure out the direction? I want to see if people get the logic here. Okay, so Jason says pi. What would happen? Where do you suspect we'll be if I plugged in pi? That's exactly halfway through the period. Yeah, so
pi over 2, I think.
Pi over 2 is a good choice. If we plugged in pi, I'll tell you we're going to get there, right? Halfway around the circle. But that doesn't help me with the direction because I still don't know if I went down or up. It's the same distance there. So pi over 2 is the better choice here to figure out the direction. You could have done 3 pi over 2 or even pi over 4 or something like that. But something that's not exactly halfway so we can see which way we're trending. All right, so in this case, x is equal to cosine pi over 2, which is 0. Y is equal to sine pi over 2, which is 1. So 0, 1 is a quarter away through this particular path. So I know that I'm going this direction. What would that be? Counterclockwise. So when we come to the final result, what is the path represented? We could say this. It is one full counterclockwise revolution or rotation about this circle. So rotation about the unit circle. Unit circle just stands for the circle radius 1 that's centered at the origin, exactly what we've got. Okay, so next one. Find the path represented by this. X equals sine of 2t, and y is equal to cosine of 2t. And I'm going to say also on the range 0 to 2 pi. So let's first of all eliminate the parameter. I'm going to do it in the exact same manner, because again, I have one sine and one cosine term. Doesn't matter that the arguments are different than just a single t, they're the same. So it doesn't matter what's in the arguments, as long as they're the same, sine squared plus cosine squared of that same thing will equal 1. If they were, of course, different, then it wouldn't work. All right, so if I had x squared equals sine squared of 2t, y squared equals cosine squared of 2t, add them together, I get x squared plus y squared equals sine squared 2t plus cosine squared 2t. You probably could have skipped that step and just looked to the fact that, again, it's going to be around the unit circle. So let's draw that circle up there. Something must have changed, right? I mean, I have this 2t in the argument, so it can't be exactly the same as before, and we'll see what exactly happens to the particle if it were traveling along this unit circle to this particular parameterization. Okay, let's start off with the initial point again. My initial point is 0. So x is equal to sine 0, which is 0. And y is equal to cosine 0, which is 1. So we start at the point 0, 1, which puts us up here. So notice that from the last example, x was associated with cosine and sine with y. This time they're reversed. It just gives you a different starting position. So, sines and cosines being attributed to the parameters will generally make you something that's circular. But if you switch them or change little things like the argument, you're going to get slight differences. Maybe the direction will be different, maybe the starting location, etc. Now, let's take a look at the direction. You can see that the final point, which is interesting, I'll just talk about it instead of writing it down. If I plugged in 2 pi, I'll get sine of 4 pi and cosine of 4 pi. And you should realize that 4 pi is going to be giving you the same values as 0 was giving you. But now it's 2 periods away, right? The argument is now 2 periods from the starting point. So even though you're back to the center, what you're suspecting potentially from that is that we traveled twice around the circle. And that's exactly what's going to happen. The frequency doubled, so the quickness of motion doubled, and we pretty much went twice as far, even though we still ended up back at the same starting point, which was up here, 0, 1. Okay. If I were to plug in a direction, well, let me give you an annoying question, I guess. What plug-in point would you want for this?
Pi over 4.
That's a good choice. Turns out that pi over 2 would give you right on the other side again, because now that's a quarter of the way through, but we're going twice as fast, so it actually gives you one full half revolution. So pi over 4 works out well. If you were to plug in pi over 2, you didn't see that far ahead, there's no big deal. It's just going to waste 15 seconds for you. And you'll say, oh, well, that didn't tell me anything. Oh, actually, it would be down here, right? You'll say, oh, that didn't tell me. I don't know if it went from the top left down to the bottom or the top right down to the bottom. I'll try something else. Pi over 4 will turn out to work out. They get x is equal to sine 2 times pi over 4, so that's pi over 2. And y is equal to cosine 2 times pi over 4, so that's pi over 2. Sine pi over 2 is 1, cosine pi over 2 is 0, so we get the point 1 comma 0. So an eighth of the way through this particular range, we've gone a quarter of the way through the circle, which means that we're essentially going to make 2 full revolutions, going now clockwise in this particular case. So final answer here is 2 full clockwise rotations around the unit circle. And that'll be your full sentence of the summary of what this particular motion does. Let's try a third one that's kind of circular, but a little bit different. And I want to show you these things that are close, but slightly different so we can learn how to build off of one thing to the next. So find the path represented by x equals sine t, y equals 3 cosine t, and again from 0 to 2 pi. I notice that this is the same orientation, basically, that sine is associated with x and cosine with y as the last one. That's going to lead to these clockwise revolutions. You don't have to memorize that. You can pretty easily figure it out by graphing. But that's, if you get into a job that requires you doing this more often, that's how you're going to get something to go clockwise. You would flip these, have cosine with x and sine with y if you wanted to go to counterclockwise. All right, so now I have a complication because of this here 3 cosine t that's in front of things. So if I directly squared both sides right now, I'd get sine squared plus 9 cosine squared, and that doesn't reduce to anything by Pythagorean theorem. Does anyone have a suggestion here of how we could eliminate this parameter?
Couldn't you move the 3 to the y?
Let's move the 3 over before we square it. Exactly, good job. So x equals sine t, and y over 3 is equal to cosine t. And now we can do the exact same trick that we did before. Square both sides, and we'll get the exact Pythagorean identity on the right-hand portion. So we get x squared equals sine squared t. Y squared over 9 is equal to cosine squared of t. Add them up, and I get x squared plus y squared over 9 is equal to, I'm just going to skip this step, sine squared plus cosine squared equals 1. We've done that now this third time. And we get this. X squared plus y squared over 9 equals 1. Does anyone know what that shape represents? So by the way, knowing all the graphs of basic things, not really that super important for Calc 2, except for like that initial stuff, volumes of revolution, but it will be absolutely essential for Calc 3. So what is something that looks like a circle, but one of the things is divided by another number over here? It is an oval, yes. An ellipse is actually the ideal phrase for this one. Oval is just a specific ellipse. But this is an ellipse. So an ellipse is x squared and y squared divided by potentially constants equaling 1, where these, whatever you're dividing by, suppose you have x squared over a squared plus y squared over b squared equals 1, these are going to be like your radii in that direction. So whatever the center is, you'd go a units left and right, b units up and down. That would be the extent of your ellipse. So in this case, you can see that my x radii is 1 and my y radii would be the square root of 9, which would be 3. So this is an ellipse. Draw it out over here. Still centered at 0, as you can see. In the x direction, we go 1 unit. In the y direction, we go 3 units. So we kind of have this shape of my ellipse. Let's graph it. Let's get the initial point. Okay. If I plugged in t equals 0, we would get x is equal to sine 0, which is 0. And y is equal to 3 cosine 0, which is 3 times 1. And 3 times 1 obviously is 3. So my starting point is x0, y3. I start up here. You see the arguments are just a simple t. So by the time I get to 2 pi, I will have gone through exactly 1 period. So it's going to be 1 full rotation around this ellipse. I guess we should figure out which direction it is, because most people don't memorize that. Rightly so. So let's just pick pi over 2 again, a quarter of the way through the period, which should be either here, right, going down half of a revolution to the right, or here, going down half a revolution to the left. So if I plug in pi over 2, I get x is equal to sine pi over 2, which is 1. Y is equal to 3 cosine pi over 2, 0. So I get down to this point here, 1, 0. You can see a quarter of the way through my range. I've gone a quarter of the way around the circle, and I am going clockwise. So make some arrows to show the whole range, and then I'll say that this is 1 full clockwise rotation around the ellipse.
Do we use pi over 2 since it was halfway through the graph? Or
not halfway. If it was halfway, I would have gone halfway around the circle and not known which direction it would have gone. So I'm using this because it's a quarter of the way around. So then when I find that it's here, I know, okay, so the particle must be traveling from the top, the initial point, going down to the right around the circle. So then I know it's going clockwise.
okay, and for the last problem, we got 2 full clockwise circles. Was it because in the equation it was sine 2t plus cosine 2t, or?
That is what caused it. But what we noticed was when I plugged in, it wasn't pi over 2 that I plugged in, it was pi over 4. So plugging in something a quarter of the way through the range, an eighth of the way through the range, led me to a quarter of the way around the circle. So there I realized that I'm going twice as fast around the circle as I did before. And there's nothing special about having to plug in this specific point. If you had plugged in pi over 4, you would have gotten a spot, here, which would have said, oh, well, I'm going this way again. And I could see pi over 4 is an eighth of the way around the circle. And from here to here would be an eighth of the way around 1 rotation as well. So you're just trying to figure out, based on a few plugins, which way it's going and how fast you're going. But yeah, the general answer is when you see things with a single variable like this with no coefficient, it's like going at normal speed. If you see something with like a 2t or a 3t in your argument, that means the frequency is increased. If you saw something like half t in there, the frequency would be decreased.
All right, thank you.
But I'm just trying to say, don't memorize completely, because what if you had something like x equals, sine 2t and y equals cosine of 1/2 t? Well, now it's confusing, because in one direction it seems like it's going faster, in one direction it seems like it's going slower. So it really is about, plugging in things and kind of using logic and a few test points to figure out what's happening. I don't think there's going to be anything too hard, but you never know.
Is there a way to figure out, mathematically, a technique to actually get the number that you should use to test? If I'm saying that correctly. So you're just kind of saying, obviously I knew in that last problem that pi over 4 was correct, but after drawing the graph and looking at all the parameters, it was just logical.
Yeah, I think actually that's the best way to do it. Just kind of go with the logic of it.
Okay.
There's nothing that's specifically right or wrong, because the pi over 4 wasn't specifically right. There was lots of different things that could have worked. You just want to avoid the thing that's directly across, because then you don't know which direction it's going.
Right. Even if you used 0.001, you would get the right direction.
Correct.
Okay, yeah, that's true. That makes sense.
Okay. So everyone got this? Gonna do another one? Gonna do a weird one now. So find the path represented by x equals sine t, y equals sine squared t. And the range now is going to be all real numbers. So we can see that Pythagorean identity is not going to be of any use at all here. There's only sines and no cosines, just sines and sine squareds. So does anyone have a suggestion on how we might eliminate this parameter? Get you thinking on this Friday afternoon. Subtract 1. Just be aware though, it's not sine t and 2 sine t. So sine and sine squared don't really subtract in any meaningful way. If it was sine t and 2 sine t, then we could subtract them.
Is there an identity here that we could use for that sine squared, maybe?
There are identities, but there's actually a much simpler way. So
Okay.
if anyone can think of a very sneaky but simple way to eliminate these parameters. Subtract 1 on each side for y. So you want to say like y minus 1 equals sine squared minus 1.
Professor?
I think that's going to be too complicated. I think you're going for cosine squared there, but don't need it.
Professor, what if you square the sine squared t on the y and then you subtract so you have x minus square root of y equal to 0?
Okay, that's the right idea. I'll actually do it backwards from what you did. You can actually just do direct substitution here, right? Because if I squared the first one, x squared is sine squared t, right? Well, now you have two things equal to sine squared t, so y equals x squared. All right. So there's a simple way. The way that Nora was going actually would have worked as well. It just would have been a bit more steps. But in this case, direct substitution could have worked. Now, what is y equals x squared? Well, we know what that looks like. That's just a simple parabola, all right? But I'm not going to draw the whole thing quite yet because there's an issue with this. When I did that substitution, I implicitly took the range of sine t with it. So, this is why I said this was a tricky one. I know that sine exists between -1 and 1, right? Sine t can only exist between -1. Therefore, x can only exist between -1 and 1. So therefore, it's the parabola I know, but I cannot go past x equals -1 or past x equals 1. Right? None of these points can possibly ever exist. So I basically have this point -1, 1, and this point 1, 1. So that's the extent of the curve that's possible. We can also see that the same issue arises with y. If y is equal to sine squared, then y can only ever be between 0 and 1, which it is if I restrict it to this portion of the path. So what does that mean? If I go from t equals -infinity to infinity. So let's figure out what the thing actually does. I'm just going to say here that y is always between 0 and 1. So what will happen is this thing just kind of bounces back and forth along this portion of the parabola, kind of like a skateboard half pipe or something like that, just going back and forth forever. As sine cycles through, sine will go from positive to negative, and I'll just go back and forth along this portion. So I'm going to say the particle, if we're talking about a particle moving along a path, moves infinitely back and forth, let's say along this segment of the parabola. So with pretty simple functions, you can get some very interesting, complicated motion. And certainly just by looking at the function y equals x squared, you can never really explain that motion. But by a parametric curve, we now have this back and forth motion along a parabola, up and down, back and forth forever. So I think that's actually kind of a cool example. I don't think you're going to be seeing ones that are that creative and hard on exams, just because it's a little bit more difficult. But it's cool to see what's possible, at least by parametric curves.
Professor, so before, you remember how you said the circle was going 2 times around?
Yes.
And was that because it was restricted by the 0 to 2 pi? That's why it moved or 2 times around?
Yes. So if we had those circular ones and my range was -infinity for the parameter, then it would just move forever around the circle.
Okay, that makes a lot of sense.
Professor?
Yeah.
Will these questions always involve sine or cosine?
No. Actually, the first one we didn't, right? If you looked at it as x equals t squared minus 2t and y equals t plus 1. And the next one we will do will also not. It turns out that we often like to parameterize things that are circular because they're pretty nasty to deal with as a regular function, right? If you look at the equation of a circle, it's not a function in either x or y. So parameterizing it does help us. So I don't want to give you a lot of things that look circular, but by no means is that the only thing that is parameterizable. And so last of these path problems, and then we'll do some other stuff. So this is a problem that is directly out of Calc 3. I don't think they even talk about it in our book, but it becomes an important one, so I want to do it now. So parameterize a path that moves from one point, -1 to 1, to another point, 3, -1, along a straight line. So now we're trying to figure out the parameterization. They tell us the path initially. I can actually draw this very easily. -1, 1, that's the starting point. And then 3, -1, that's the ending point. But this path moving from second quadrant into fourth quadrant, basically. So, I mean, I know it's a straight line, so I might as well figure out the equation of that line, and then we can try and figure out parameterizations from that. So that's what we're going to do. Let's figure out the equation of this line as a regular function, right? I can write it as a function easily. So I'll need the slope, which is delta y over delta x. Rise over run, essentially. So change in y is 1 minus -1. Change in x is -1 minus 3. So I get 2 over -4, or -1/2. So that's my slope. So if I wrote in point slope form the equation of a line, it's this, right? It's y minus y naught equals the slope times x minus x naught. And obviously I've got 2 points, so I can easily plug in y naught and x naught. Either one of them will work. And the slope I have now found. So I got y. Let's use the first one. So y minus 1 equals slope, which is now -1/2. X minus x naught, which is a -1, so x minus minus is x plus 1. Here I'll just note that I defined my x naught, y naught to be -1, 1. Could have used 3, -1 just the same. It's like y equals -1/2 x, -1/2, and then I'm adding the 1 over. So y equals -1/2 x, -1/2 plus 1 is plus 1/2. That's the equation of the line. But that doesn't quite help me with the parameterization yet. That's the next step. I guess any question with the algebra portion here? Finding the equation of the line. So here's how to parameterize a function. Actually, anything that can be written as a function is trivial to parameterize. And a lot of people forget this in Calc 3 and they get all turned around trying to parameterize in such weird ways. Because what I can do is if I have a function, is I could just let the independent variable be the parameter. So let's let x equal the parameter t. Right? Now y would then therefore be just -1/2 t plus 1/2. Done. It's parameterized. So any function can be parameterized in a very similar manner. Sometimes they'll actually just not even write t anymore. They'll say, well, let's let x be the parameter. So I'll say x is equal to x, and y is equal to -1/2 x plus 1/2. A lot of people don't like that in Calc 3, that it confuses them. But it's the same thing, it's just calling it a different letter. I'm going to stick with the t's just so we can see it more clearly. But I do need a range for the parameter that defines that specific line segment. Well, I know that x is just t. So when I need the parameters range, I just need x's range. And I know that x goes from -1 to 3. So that's it. That's it. This is the range of x, but x is equal to t. So it's actually very easy to parameterize something like a line or a line segment. And you'll have to do that a decent amount in Calc 3, especially Calc 3b. All right, so where are we? 330. So I think we're going to start 11.2 because it's a long section, just so we can finish it in time.
Professor, are both endpoints included?
Yes. So if it moves from -1 to 3, -1, that means it actually goes from that point specifically to that other point, so then we would include the endpoints.
Got it.
I don't even know how the problem would be worded if it would not be included. It'd be very awkward to write, actually. So usually you're going to include endpoints here. All right, so any question there? Otherwise, we'll start off with 11.2. There's no homework for 11.2 due. So, or at least not this week. But like I said, it's a long section, so let's just get a little bit of a jump on it. It's called Calculus with Parametric Curves. So, that was the easy section. It's just basically kind of graphing and exploring and playing around. Now we start to say, let's do all the things we did in calculus with a parametrically defined curve. What is the slope at a specific spot? What is the integral under a parametrically defined curve? Et cetera, et cetera, et cetera. So what we're going to do today is we're just going to derive the formula for the slope, dy dx, of a parametrically defined curve. So it's not too bad of a derivation. It's a little involved. I'm going to call the parametrically defined curve C, just as I refer to it later. And I think we'll just get to the formula and then call it a day. We'll start using it on when do we meet next? Tuesday. Okay, so let's define C. So let C be given by these parameterizations. X is equal to some function f of t. Y is equal to some function g of t. Now, what we're going to assume in this problem is that we can eliminate the parameter somehow. All right? So let's just assume we've done that and we'll name what that resulting function is. So by eliminating the parameter, we can express C this way. So by eliminating the parameter, we can express C as this function. We'll say y equals some big f of x. And it may be very hard to figure that out, but we're just doing it in a general form so we can find the slope equation. And if you're able to write it in this way, y equals f of x, then it's just a regular function. So I just need derivative of that thing. But I need the derivative in terms of t. So we're going to find the derivative of this dy dx, but then translate that in all terms of t. So we need y's derivative, but in terms of t. And that's our goal right there. So if I need everything to be in terms of t, let's write everything in terms of t, which is let's get rid of the x and the y by the parameterization. That's the whole reason we have it. So subbing in, we get the following. So we get y, which is g of t, equals f of x, but x is f of t. So make sure you're writing these f's differently, right? There's the little f, which is the parameterization of x with respect to t, and there's the big F, which is the function if I were to get rid of the parameter. So I get this now. G of t is equal to big F of little f of t. And now I can differentiate. So let's say implicitly differentiate. So this literally taking the derivative of both sides. Derivative of g of t is g prime of t. Derivative of this, so this is going to be a chain rule because there's an inside piece. So it's big F prime of f of t times the derivative of the inside. So the derivative of little f of t is f prime of t, whatever that is. And remember what we're going for here is we're trying to find f prime, right? The derivative of y, which would be f prime. So I have to solve for this at this point. And I'm also going to note that f of t is x. So basically I'm getting big F prime of x. So f prime of x is equal to f prime of t over g prime of t. And that's it. That's basically your answer. I'm going to write it a little nicer. But to find dy dx, I take the derivative of the x function and divide it by the derivative of the y function in the parametric equations. So this formula essentially allows us to find dy dx without ever eliminating the parameter at all. So you get the derivative in terms of the parameter directly without ever having to consider what the original function and what its graph looks like. So here is put in a box the final results here. So the slope of a parametric curve looks like this, right? So dy dx, the regular derivative is going to be dy over dx dt. As long as dx dt doesn't equal 0, which there's your formula. It looks actually algebraically like it would just cancel out, right? If this dx and dt were separate things, it looks like the dt's would cancel and you get dy dx on both sides. So the notation that Leibniz came up with is a good one. I'm going to put another equation, which is more annoying, but similarly derived, basically doing the same stuff, is what's the second derivative with respect to the parameter? So d2y dx2, the second derivative of y with respect to x, ends up being something you wouldn't expect probably. d dt of dy dx divided by dx dt. So I'm going to put that in like a dotted box. I don't find it that important, but sometimes they do ask it on the final, so I guess just memorize that for that particular test. So what this is saying, once I find dy dx, take its derivative with respect to t and then divide again by dx dt. So the example for this, I don't think we're going to do now because it's Friday afternoon already, and we just had our exam this week. So unless there's any questions, I'm going to leave it there. All right. Otherwise, have a good weekend. We have no quiz next week, so you can kind of just relax, catch up on the homework, and away we go. But let me know if you got any questions.
Bye, Professor. Bye, guys. Have a nice weekend. Stay safe. Bye.
Later.
Have a good one.
Be safe, Professor. Bye, everyone.
Enjoy the weekend.